So I now request Neha to introduce our speaker.
Dr. G. Unnikrishnan is a senior professor in the Department of Chemistry of NIT Calicut. He has received his PhD from MG University, Kottayam, Kerala. His postdoctoral experience includes the assignment as an environmental specialist at Abu Dhabi. He possesses experience in academia, industries, in teaching, research, and administrative domains. His current research interests include design and development of novel macromolecular architectures, synthesis and characterization of pi-conjugated polymer systems, nanomaterials, polymer blends for biomedical applications, polymer metal organic frameworks, natural fiber reinforced composites, polymer membranes, tribopiezoelectric materials, and novel catalysts for organic reactions. Dr. G. Unnikrishnan has supervised 33 PhDs. 11 scholars are currently working in his group. He has authorized 271 technical articles with 4,240 citations. He successfully completed 12 research projects funded by MHRD, DST, STEC, CSIR, British Council, etc. 5 patents have been derived from his group. He is a recipient of Professor Shankarlal Memorial National Award, IIT Kharagpur, and Best Performer Award, NIT Calicut. He has current collaborative programs with different universities and institutes. He is a fellow of Royal Society of Chemistry. He is a member of American Chemical Society, International Union of Pure and Applied Chemistry, Materials Research Society of India, and Indian National Congress Association. He is the founder, secretary, and current president of the Calicut chapter of Society for Polymer Science. Now I invite Professor G. Unnikrishnan to deliver his talk on biocomposites.
The request is that please get involved in all discussions, have questions. This is your home. Do not keep boundaries. So whatever doubts you have in mind, please float it so that we will discuss it. And in the afternoon, this is the morning sessions, we will be sitting in the classrooms to listen to the lectures. Afternoon session, we will be moving to laboratories. So in this afternoon itself, you will learn how to make a composite, biocomposite. And in the next 2 days, next Tuesday afternoon and Wednesday afternoon, we will be having exposure to different equipment like IR, UV, NMR, DLS, and many, the DSC, TGA, etc., etc. 2 sessions will be splitting into 2 groups in the afternoon. So we'll be having, it's a tight schedule, but we will complete it in 2 days' time. Thursday we'll be having a site visit to Wakru, this the Indian top tier chapel manufacturing unit. And then in the last day we'll be having a consolidation of our thoughts. Dr. Alan Jefferson would be doing that. So this is the overall program. So some of you may be having an exposure to biocomposites by now. But if you do not have an exposure to biocomposites, this session is dedicated for that. So in our laboratory at NIT Calicut, we basically work on materials. Biomaterials, materials which we see, plants, anything we see in nature, biomaterials. Sometimes biomaterials should be complemented by some materials which are to be synthesized in the laboratory. Therefore, our students synthesize some molecules. So we focus on 2 types of materials, molecules or materials given by nature. Cellulose is a type of molecule, big molecule, which is being given by nature. But to do value addition to cellulose, we make some small molecules in our laboratory. Meaning, some molecules are made in the laboratory, synthetic, some molecules are given by nature, natural. So we integrate them together. Sometimes we work with them independently, sometimes we integrate them together to generate new types of materials, because materials, almost all innovations in the modern world are closely connected with materials. So if you develop a new material, you will be contributing to the electrical field, electronics field, mechanical, civil, etc., aerospace. So as material scientists, we have great jobs to do. And I guarantee you, if you have an exposure to biomaterials, you will be having big contributions to the society. That will make your life more productive, and that will make your life more filled with happiness. And that is the target of our assembly here. Shankar, good morning. So if you look to the wider domain of materials. We all material people work basically we work on three types of materials. One is metals. Metals we all know metals. Aluminium, iron, gold, platinum. Lot of materials are there in the periodic table. Sometimes we work with ceramics. Ceramics means bricks are ceramics. Tiles upon which we walk, they are ceramics. Second type of materials. Third type of materials are polymeric systems. Natural polymers and synthetic polymers are there, bigger molecules. Sometimes we cannot meet our expectations with a single material. Therefore, we mix them together. You might have heard of a technique called alloying, ALLO. Alnico is a combination of aluminium, nickel, and cobalt. Why do you go for that? Because you are not happy with the performance of aluminium alone, or not happy with the performance of nickel alone or cobalt alone. So you integrate the features of aluminium, nickel, and cobalt. You make a new material. You present a new material to the world called Alnico, having the integrated features of aluminium, nickel, cobalt. That's called alloying. In polymeric technology, the term alloys is used, but we use another term called blends, polymer blends. You take one polymer, take another polymer, mix them together, you call it as a polymer alloy. And a major field, but that's the focus of work, is called composite systems. Very highly fascinated system called composite systems. Abdul Kalam sir had a dream on composites. So he started a composite technology center at Trivandrum, capital of Kerala, which is completely supporting the operations of our space research and space achievements. So composites play a major role in space technology, medical devices, kitchen appliances. So these are the new generation materials. And when the composites are derived with the support of biomaterials, we call them as biocomposites. And we'll be so metals. You will be quickly seeing the features of all these materials. So metals are typical materials having features like malleable. They are malleable, tactile, high electrical conduction, thermal conduction, right? Metallic luster, etc. So we need these properties for some engineering applications. There we do not have a substitution for metals. Metals should be used for that. Where the construction, as a chemist, when we look into that, the metallic construction is something different. Metals are made out of nuclei, and large number of electrons float within that float. Large number of nuclei are presented here. No electron belongs to a special nucleus. Electrons belong to all nuclei. Electrons are happily running. Electrons are running, and the running electrons are the postmen for the conduction of heat and electricity. So that's the assembly of metals is something totally different. Charming properties of metals. If you look into the second category of materials, which are basically inorganic metallic oxide, nitrates, carbides, etc. We use them. Even our wash basin is made out of a ceramic material, right? The beautiful tiles at home are made out of ceramics. And many of the furnaces, typically we have heard of blast furnace. Blast furnace is having an inner liner. That liner, no material can be made out of that inner liner, only a ceramic, because the temperature would be going to 2000 degrees centigrade. So you will be having no substitution for that. If you will be having no substitution when an inner fabrication of a furnace is required, only ceramic can be seen. We have seen in our old home, our grandmothers used to make water. So always they use bricks to make the furnaces. Small furnaces at our home are made out of bricks because they can withstand very high temperature. So conduction, electricity, metallic resistance, etc. are the priority. We look for metals. If thermal resistance, height, etc. are the liner fabrication of a furnace, etc., ceramics are the priority. Then we move to the third category of materials called polymers. These materials are having a beautiful assembly. We all know small molecules. But then scientists thought, if small molecules are connected together, why can't we make big molecules? Independently, we all are weak, but if we collectively sit together, we are strong. That's the basic principle of the construction of polymeric materials. When a substance is having a double bond or two functional groups, in a molecule, that molecule can be polymerized. Single molecules, saturated molecules cannot be polymerized. Methane, there is no methane is alone. Methane alone is stable. It does not have the tendency to connect with a second molecule called dimerization procedure. But ethylene is having a double bond. I mean, right? Therefore, you can combine two ethylene molecules together to form a diethylene. This procedure is called dimerization. When you take three molecules together, it's called trimerization. When four molecules are together, tetramerization, pentamerization, decamerization, and finally beautiful polymerization. So gem clips are connected like that. Connected. So that it's a strong system, Some of the gem clips are vertical. They connect the chains together. That is called cross-linking. It's just a beautiful architecture. We have this just like an architect making a beautiful building. So no homes are identical. My home is different from the neighboring home because the architecture is different. The architect has applied the mind. All the houses are made out of bricks, but bricks are aligned in different directions. Designs are different. That is the logic in polymer science. So you have some molecules, just like kids making toys they make, we can connect molecules in different ways and see the happiness of the molecule he or she derives. That's called polymerization. Combine small molecule. This is the focus of our program. So what we do is ethylene. Ethylene is when it's subject to dimerization, you get diethylene. And a trimerized with three molecules, tetramerized with four molecules. You see, when you do that, length is enhanced to nano dimension. An atom is one single atom is or a molecule is in atomic dimensions. Single atom or a molecule is in angstrom dimension, angstrom 10 raised to minus 10 meter. But when the 10 of them combine together, we enter into nano dimension. 10 molecules, 10 into 10 raised to minus 10 is 10 raised to minus 9 nanometer. That is 1 nanometer. So we enter into nano domain. Polymer science is nanotechnology. Combine molecules together to nano dimensions, 500 nano dimension, 1000 nano dimension, etc. When we make such molecules, they will be having spectacular electrical properties, mechanical properties, magnetic properties, etc. etc. You can modulate that. So this is the logic. Small in a reactor, just like dreams flying, molecules fly. They get together and we make low molecule. You can see in the background older molecules getting deposited. So this is the job. People live for that. Make molecules which others have not seen. That's the dream of a scientist, making molecules or making systems which others have not seen so far. Every evening they pray, help me to make a molecule which others have not seen. That's my contribution to the society. So we have now there. Why do we make such molecules? Because such molecules are useful to society. We all live for supporting the society, to support poor people, to support weak people, to make a better world. So we do that we do not have anything. We do that by contributing, by making new types of molecules in the field of automobiles, building materials, consumer goods, in the space products, etc. etc. We live for that, making new types of molecules. So now I will be telling you a strategy we do in, just like I said, do a polymer blend, to take two molecules together, mixtures of two molecules. So X and Y, two molecules are there. X is a polymer, Y is another polymer. I try to mix them together. I will be getting sometimes a product like yellow, sometimes a product mixed together, sometimes another type of product. When X and Y, green and yellow mixed, sometimes I will be getting a completely miscible product, yellow. I'm highlighting the prospects. When two materials are combined, they can be combined in different ways. Therefore, different types of products can be derived. Sometimes the product could be completely miscible. Sometimes could be partially miscible. Sometimes it could be having independent, they are immiscible. When we do that procedure, the products they make will be having different features, and therefore they can be employed for different types of applications. We have now. So if you look into that, there are different types of how to make polymer systems mixed together. This session, we will be focusing in this session, in the subsequent sessions, how to make different types of polymer combinations. But that's not our focus now. Our focus is composite system. And then biocomposite systems. Composites are, you take a polymer, you take a polymer, you take a polymer, you find that that polymer is having some inferior properties, inferior lower properties. What you do is, you identify a powder or a fiber and then carefully add it. We will do it in the afternoon. You have a polymer with you, but you find that it has some inferior properties. What you do is, you add a powder into that or a fiber into that, mix them together. You will be getting a product. See this product. You look into this product, this right hand, extremely right hand side. You see an outer layer. Outer layer is a polymer, but inside that you will be having different types of materials you add. Sandwich it. So now we will be having a new material. New material. The polymer, weak polymer now becomes strengthened. So the polymer substance we make is known as a matrix. The basic material which is to be modified. Basic material which is to be modified is called matrix, matrix, with which you modify, that is known as a reinforcement. With which I am the matrix. Since you are here, you support us, therefore you are the reinforcement. When we work together, we develop a new material. So a matrix, that's the equation. A matrix plus a reinforcement gives a composite system. You can take polyethylene, polypropylene, any types of rubber as the matrix. You can take titanium dioxide nanoparticles, SiO2 particles, carbon particles, multi-walled carbon nanotubes. Anything can be taken as reinforcement. See, hundreds of combinations are there, hundreds of combinations. Me and Amina, we combine together to make a composite system. Me and Ashwati make another composite system. Ashwati and Amina makes another composite. See how much of combinations we can make. Logically, depending upon the requirement. When the client comes, we ask, what do you want? I want a set of properties. So we'll become, she's having that property, combine them together. So that's the logic in composition. Combining materials judiciously, that depends upon your passion for doing science. So large number of products are sitting on the left hand side, large number of products sitting on the right hand side. So make suitable combinations you will be making. That's the basic philosophy in making composite system. Combine them together. And then, if any of these material are from nature, the composite is known as a biocomposite. If any of this material is obtained from nature, or it is having a term property called biocompatibility or biodegradability or something contributing to the environment, you call it as a biocomposite. So did you understand the basic philosophy in composite? You mix two materials together, you make a composite system. And if you have the features like biocompatibility, biodegradability, etc., and environment friendliness, etc., you call this material. Thereafter, your composite is having a separate title. I am no more a single composite. I am known as a biocomposite. So it means I can function for an application space. I can function for an application anywhere in the world, anywhere in the universe. I can function as a product in your kitchen. I can act as a product in your spacecraft. I can act as a product in your surgery, in your surgeon's theater, operation theater. I am not a composite. I am known as a biocomposite system. So this is the basic philosophy. You take a fiber or a powder, is added into a matrix. You can see the morphology. You can see the structural, beautiful structure, right? Many changes happen. The morphology, the structural aspects get changed. Thermal features get changed. Mechanical properties get changed. Electrical properties get changed. Optical properties get changed. Biological aspects get changed. So you do complete alteration to the basic material and you have a new material which is known as a biocomposite system. So you can have the composite system playing is wonderful. In the new modern world, lot of areas are there which need our attention. So you can have, as I said you, carbon nanotubes, graphene, zinc oxide, nanohydroxide. So any type of systems can be reinforced into the system. And if you judiciously select bio partners into that, systems which will index bio properties, nature, environment friendliness, etc., you want to call them as preferably biocomposite system. Such systems are used for making large number of products. Some products in space, some products basically some piezoelectric system. If time allows, we'll be speaking to you on piezoelectric systems being derived from biocomposites. Lot of biomedical applications. The products can be derived. A lot of products can be derived from this composite system. So you have you can have as I said, a lot of options are there. You can take a rubber or a thermoplastic or a thermoset. You can take a particle, you can take a fiber. Basically, hundreds of combinations are possible in the field of biocomposite system. So such products are being used. Boeing uses biocomposites. Benz car uses biocomposites. Helmets, lot of civil construction, mechanical people, electrical people, all the people use biocomposite system. They try to replace the conventional synthetic material system using more environment-friendly material, light materials, high-performance materials, corrosion-less materials. So these are telecommunication towers. So we have a lot of applications in the field of biocomposite system. So we'll be having this is a beautiful biocomposite system. I'll show you. So it contains, now you can see that this is the basic matrix. So this is we cannot have a physical difference. Sometimes you can see which is the matrix. Sometimes you can see which is the matrix, which is reinforced. Sometimes if they get uniformly mixed, sometimes your eyes cannot detect that. But in the microscopic scale, using a scanning electron microscope or transmission electron microscope, you can have phase separations found. So we'll in the subsequent days, we'll be seeing that. So sometimes composites, generally by earlier definition of composites was you can have phase separation distinctly, you can identify, but now you cannot do that. They get integrated in many of the systems, particularly nanocomposite systems. So we will have in a biocomposite system, the matrix and the reinforcement, they have distinct roles. Typically, you have heard of banana fibers. Banana fibers. They're beautiful fiber. I have a friend in Wayanad who he has banana cultivation. He will give you banana free, but he will not give you banana fibers because banana fibers are having a cost of 120 rupees per kg in market. He'll process it and he is making more than 5,000 products. So the products are banana. You know that after the service period, banana fibers can be sent into the environment. But banana fibers are foldable. The structural integrity is not there. You cannot make a rigid substance. For that, the matrix is added. With the matrix will be giving a shape. That is the role of the matrix. The matrix will be given the shape, etc., etc., etc. But the strength and other properties will be modulated by the fiber, by reinforcement you use. So matrix has a function for structural integrity, and the performance factors are being contributed by both of them. And now, so this is one of the major reinforcement views. Wood you have seen, no? Wood can be converted into different forms. Wood can be powdered. Wood can be powdered, very high strength. And that can be added to a polymer matrix to make a composite system. Many of the products are being derived from that. So you have heard of plywood, You have heard of a term called plywood. Plywood means, ply means layers. One layers, thin layers of fiber, etc. But they are being joined by a polymer. So the polymer acts as adhesive. If you compress it together, you'll be getting a system. Multi-layer system, high performance system. So you can see that you can take it in the you powder it, bamboo into powder form. Bamboo. See, in Kerala we have a lot of bamboo fibers, Powder. You can use it in the fibrous form, you can use it in the powderous form, and add it into a polymeric system. You can have a basic material which can be molded into any shape, you say. So in this room, you can see how many products are there. AC is there, fan is there, desk is there, chair is there, platform, dice is there. You can see that you can find out how many products in this room can be substituted by a composite system. So you can induct, when you make a reinforcement, what you are doing is you are doing wonderful engineering. You can induct a large number of properties, including smart material. You have heard of shape memory. Memory effect is there. Memory. Materials can be having memory effect. Rubber is having a memory effect. If you stretch a rubber band will undergo, when you apply a deformative force, you will go deformation. Stress is proportional to strain. Hooke's law. do that, undergoes deformation. But the rubber band does not like it. The moment you release the stress, it will try to, oh, this is not my shape. I will go back to my memory effect is being operated by materials. Many of the matrices can be inducted with a memory effect when you do different types of careful combination of different types of systems. And this is the ideal example of a biocomposite. Best example of a biocomposite, you are a biocomposite because you two components are there in your body. Flesh is there, no, that's the matrix, and your bone, skeleton, bone, that is the reinforcement. So integrate them together. Eiffel Tower, France. Eiffel Tower is having construction. The basic philosophy Eiffel Tower derived from our body, right? So this body is a wonderful biocomposite system, triggering many engineering thoughts, many scientific thoughts. So you can see the reinforcement, you can see the flush added composite system, right? So basically, when you do that in all calculations, you have a, this is the rule of mixtures. Composite is a marriage, husband and wife system. Husband and wife. Husband is alone, wife is alone, then that's not a family. And when someone marries a girl, we become a composite system, matrix and reinforcement. Thereafter, they are known. So husband has a contribution called sigma m. Any property of the composite, sigma c, this is called rule of mixtures. Any property of a composite, why do you make a composite system? Because of the sigma c equation. Sigma c, any property you can derive for a composite system that is contributed by husband and wife. Sigma m is the property of the husband. Phi m, what is called phi m? Phi m is the volume fraction. How much of, what is the quantity of volume fraction, just like mole fraction. Mole fraction maximum value is 1, running between 0 and 1. All fractions are running between 0 and 1. Therefore, you will be have, if phi m is 0.6, definitely phi f is 0.6. If phi m is 0.3, phi f is 0.7. Right? Maximum value is 1. So, that property of the matrix into volume fraction of the matrix plus that fraction of the fiber into volume fraction of the fiber, that favors the property of sigma c. So, this is the basic philosophy. If you are employed in NASA, or any organization, they ask you to make a composite system, the strength calculations are always based on this. You will ask me, sir, what is your targeted sigma properties? They will tell you, these are the targeted properties. Then, based on that, you will be making the volume fraction set, right, depending upon the requirements you have. So, this is the, when you make a composite system, this is the logic in organization. The fibers can be aligned. Fibers can be aligned. You get the square, the rectangle or square is the matrix. You can see lines, vertical lines, horizontal lines, etc. etc. That's called alignment. You can have a horizontal alignment, vertical alignment, and horizontal and vertical alignment together. Depending upon the strength requirement, you can have the different types of alignments. So based on the alignments, you make different properties. Directional properties can be derived based on this alignment in a composite system. With a powder, you cannot do that because powders do not have directional nature. You can make multiple plies. That's what that I said, you layer, plywood, layer wood. So depending upon the strength requirement, etc., you can have different types of layers. Just not move now, Gobiga. So this battery is. Yeah. Now, quickly I will tell you this slides, afternoon half an hour session, I will tell you how to make a but before that my professor would be enriching with how to make a composite system. But I will include these slides, this next 7 slides, how to make composite making can be right from with your hands, you can make a composite system, and to the field of 3D printing. We will tell you the 3-dimensional printing, the modern additive manufacturing. In the afternoon, I will tell you how to make them, but before that, professor would be telling you many things. And afternoon, before doing the laboratory, we will be speaking to you on the composite system. So these are wonderful techniques. We will do that. Injection molding, extrusion, blow molding, how to make bottles. It's called blow molding. 3D printing, you can see that. So anything can be. And then we look into the, so that part is so, we understood what is a biocomposite now. Secondly, we said of the alignment. Then we said of the composite making technology, which professor will be explaining to you in the second session. After that, I will be supplementing some notes in the afternoon, right? Then when a system is made, before I present before the clients, I have to convince myself what are the properties I gain, what are the mileages I got, mechanical mileage, rheological mileage, thermal, electrical, solvent resistance, optical aging. And this is our target for the laboratory sessions. We'll be looking into how the features are being evaluated by different techniques. This will be afternoon. And then we will be looking chemical properties, will be looking whether this substance, the new composite we made, will be undergoing oxidations, unwanted oxidations. Sometimes whether it will be undergoing combustion reactions. Sometimes it could be undergoing a degradation. That evaluation also has to be done for a composite system. So we said of what a biocomposite is initially, then we said of its alignment, then we saw quickly the fabrication properties. Then we saw the what are the characterization protocols we are using. After passing all these stages, we will be entering into the field. After I have made a beautiful molecule. For whom? For what? If it is having some value, it should be useful to the society. For that purpose, I will be scanning the different biomedical properties could be evaluated. So we will be using whether this biocomposite can be used for making a scaffold for some tissue engineering, some body parts, any implant can be derived from that. So that's my investigation. Sometimes so many of the natural polymer systems, collagen, chitosan, alginate systems. So we are extensively our group. We can scan the literature from our group. Deverson's group is a very powerful group. It will a very large number of citations, very powerful papers which influence the world from his group. You can see, you can read. We definitely, if possible, we will give the links of those papers also with you. So that when you sit alone, scan the papers. And in what way, through biocomposites, you can serve the society. Integrate your thoughts into that. See, say if someone is having some orthopedic requirement. Someone is having orthosis. Some people may not be having hands or legs, etc., etc. You can develop some systems. You can combine some mechanical features into the system. You can beautifully modify. You can support the society. Bone regeneration, orthopedic implants, wound healing applications. Many of the systems are being derived from this biocomposite system. And another major area of application biocomposites is pseudo membranes. Singapore and Malaysia. Singapore and world's very powerful country, Singapore and Malaysia. They do not have even a drop of water to drink. If you go to a home at Singapore, they will not give you water free. They will give you Coca-Cola free, but they will not give you water to drink because they do not have water. Therefore, that was the converting disadvantage into an advantage. That is the job of a scientist. So they have started developing high-fi membranes. They are the leaders of making membranes in the world now. In universities, many of the professors are having connectivity with membrane companies, and many of the membranes are now being developed out of biocomposite systems. Second application, and optical applications. You have seen that all the communications in the world now, many of the communications are happening through optical fiber cables. You might have seen OFC. OFC is having a core and a cladding. Communication happens to the core. The procedure is called total internal reflection. So in Gulf countries, you might have seen this long wires coming. Light is sent from one tip. The light comes from outside. No loss in between. You have seen that, no? So optical fiber cables. So the procedure is called total internal reflection. The cladding does not permit light to go out. Complete internal reflection happens within the core area. So, and many of the biocomposite systems are being tried for making optical fiber cables. Another very major property is called light emitting diodes. All the lights completely in the room would be light emitting diodes, based on light emitting diodes. They're having the NP junctions, which are polymers, many of the conducting. In between, you will be sandwiching, in an NP junction, you'll be sandwiching it with a biocomposite system, which can give you more energy protection, energy performances. So light, and then solar cells, energy capturing. In solar cells also the middle layers you have seen, polymer one layer, polymer two layers. People are investigating, they are being made out of many of synthetic materials. They're trying to replace them with biocomposite systems so that the equipment becomes user-friendly, operation becomes more eco-friendly. And this is a major job we are going to discuss over the 5 days. And if by the end of the day, if you feel that Oh, this is a wonderful field, and I can also make contributions to it. If you have such a thought derived, you will rate this program a big success. So, thank you very much for the first session. Thanks to Gian's team. And I have taken information from different textbooks, websites, etc., and big thanks to them. Thank you all. So, this is sharply we complete by 10:55. The process session will be starting by 11. And in 5 minutes time, if you have some queries, we would be glad to discuss. Queries, make queries a part of our program. Any question you can ask. Please. Queries, please, come on. Make a habit, do not hesitate to ask questions. Please, come on.
So,
Yeah.
apart from biodegradability, etc., what are the properties which are contributing more towards biocomposites than conventional polymers or conventional composites?
Right. It's a very good question. Functional performance is the ultimate target. Functional performance is the ultimate target. If you can replace a new, say, existing material with a new one with high performance, market will accept it. Point number one. Point number two, even though you are providing a solution, if it is against the environment, market will object now. So you have to have a rethought on the performance. Performance is good, should be there, otherwise no one will accept. Same time, how does it support the environmental operations? How does it, typically when you design a material for my body, blood circulation should not stop blood circulations. It should not prevent cell growth. It should not cause any damage to my body. So all these properties are to be integrated. So biocomposites are not simple. Bio-functioning is not the target of a biocomposite. High performance is a target. Environment friendliness is a target. The compatibility with the other functional systems is a target. Multiple targets are there. A biocomposite will become a true biocomposite only when we meet all these targets. And we will be seeing the answers to your wonderful question in the coming sessions. Thank you. More questions, please. Come on. Come, please. If you use a mic, that would be useful to others. Yeah. So prepare questions. We expect 3 more questions. Yeah.
So when we are reinforcing a matrix, you said about unidirectional, bidirectional, then
Yeah.
unidirectional, discontinuous and all.
Yeah.
How do we make it in that particular way?
Oh, beautiful
Is
question.
there,
Yeah.
is there any like instrument, or do we like use our hands-on method or something of that sort?
See, that's what you do. What you ask, how we make the alignments in the system. It's a difficult job. Typically, one procedure is their hand lay, where you can keep with your own hands, you can align them and put the resin and then make it. Another technique is called this, a filament winding technique is there. ISRO does that. So on a mandrel, you'll be having controlled orientation done system, meaning mechanized systems can be used for orientation and manual systems can also be used. Orientation is slightly difficult. Random systems are easy. But if you have random definitely, because that is easy and reasonably they're good too. But if you want to make an alignment, it should be done carefully. There are systems to do that. Then, more questions? No questions? Please, you have some questions? So if you have no more questions, we'll wind up the session. And thank you very much. Take care. So, over to Professor Diffs. Yes, yeah. We want to have some break, no? You can relax for 2 minutes. By that time, we will prepare. Continue.